Okay, we're ready for our next speaker. Joining us is Reuven Bakalash. He is CEO of Adshir. You know, ray tracing it's been around for, is it decades now? Like the concept is even older.
The concept is from 16th century.
Oh my goodness. But as old as it is, it tends to require a lot of horsepower.
Right.
And wouldn't it be amazing if there were new ways to look at this? So let's give Reuven a big round of applause.
Thank you very much. As Neil said, a new way looking at it, and I would like to look at it from the perspective of of the graphics, of the gaming market. So, okay, so it's very natural to address clouding or cloud from a perspective of gaming industry, which is a huge industry. Today it's about $150 billion, which is huge. So it makes sense to talk about it. And I would like to ask two questions. One question is immersive graphics. How can I get immersive graphics for the gaming industry, of course? And the second question is, let's say we have this immersive graphics on high-end computers. Can we move it to the low end, to smartphones, to tablets? Is it possible? So these are the two questions. Now, what does mean immersive experience? Everybody knows about augmented reality. Augmented reality the principle is very simple. Now, the target is how can make the user to believe that what he sees is real. There's a problem. It's a big problem. Because our mind can't believe in something which is not real. Let's look at this picture. This is a dinosaur on a table. Okay? So it's very hard to believe that this is real. But the dinosaur is in an environment of glasses, of walls, of mirrors, and so on. Now, we have to create an interaction between the dinosaur and the environment. Now, look at these glasses. This glass and this bottle, they are real. And you look at the dinosaur like something real because it looks like real. Now, this cannot be done by regular graphics, which is called raster. Raster is very fast. It's a very fast graphics. It's very cheap graphics. It's all around, but it just cannot make it. So who can make it? Ray tracing. Ray tracing is I wouldn't say a new technology, because it's not new. It's an old technology. I know it from the beginning of 90s. And it always was considered as something that has a future. And people joked that it always will have a future because it's so hard to get it, so it always will be something to talk about, but not to get it. Today I'm going to show you that it's coming, it's getting real. So what is ray tracing? Ray tracing is a simulation of light. If you look at this hall, for example, why can we see each other and the tables and everything? Because there's light. If there's no light, you cannot see nothing. You will see nothing. It's not light. Now, how do you simulate light? You simulate the light by billions of rays. Now, the scene is a bunch of triangles, millions of triangles. And then billions of rays are shot from light sources or from the eye, doesn't matter, and they penetrate the scene, and then you have to find out for each single ray what is the single triangle that is hit by this ray. Now, in order to find this triangle, you have to check many triangles on the way. So it's a repetitive intersection test. Finally, you find it, but this is just for single ray. Now, once you find the triangle, you have to find out what object it is, what material, what color, and so on. Is it glossy? Is it reflective? And so on. So this is just one hit. Now, this is one hit of one ray, but then this hit generates a secondary ray. This was the first ray, the primary. Then there's a secondary ray, which bounces somewhere in the scene, and then next ray, next generation is created, and so on. And you have billions of it. So it's a quite large task. That's the problem. So you see here, we can see a scene which is built out of triangles. And after ray tracing, you will see the whole thing right there. So the second question, so the first question we know, we need ray tracing. The second question is how to bring mobile AR, VR gaming into line with high-end pieces. So maybe we can make it on high-end pieces, but how can we make it on a mobile? So this is a kind of example. We will see the next slide. I'm going to show you a video which is generated on a high-end PC. This is ray tracing. And we will see that this is very complicated ray tracing, and then we will see that the same scene can be generated on a small table, on a low-end computer, a tablet. So let's look at it. This will be a scene which is a kind of typical scene of a game, which is 150 triangles, 20 textures, and it's running on big computer, I mean a high-end PC, 60 frames per second. Then the same scene exactly, little bit modified, reduced for less triangles. We'll have 70K triangles, 14 textures, and it runs on a tablet 15 frames per second. But it runs. And you see the real life picture. So here it is. This is raster. This is raster, and this is ray tracing. You see the difference? So you see reflections, you see real time. Once again, raster and ray tracing. And this is running, this is a very heavy stuff. Some 10 years ago, you would need thousands of CPUs working in batch, offline, to generate this stuff. Today you can see it in real time on a PC, and then on the same on the tablet. Okay? So this is ray tracing. Now, let's talk about rays and clouds. We need the client and we need the server. What we are going to try to achieve is intelligent client, self-sufficient client in the cloud. So client which is not a dumb client, but client which can do work by itself. But for heavy tasks, maybe we will give him some assistance of the server. So it will be supported by the server. And we would like to have a cross-platform ray tracing, which means cross-platform means that you can run the same software on different platforms, different GPUs. And server, we want to be a low-cost server, large number of concurrent streams, power efficiency, so low power, to save power, and low lag, fast throughput. So let's see if we can reach it. So a little bit about brief history of ray tracing. This is an old stuff. In the 16th century, Dürer, a painter by the name Dürer, invented actually ray tracing. He didn't know that this is ray tracing, but that's exactly what he invented. So the idea is the same idea as today. So this is the painter looking at the scene through a grid. It's like sending rays into the scene. Today, we have almost the same, but digital. So what we have is an eye sending rays. We have a grid of pixels, and we have a scene. The scene is a binary scene, and you shoot into the scene. So the same idea. And the first to use ray tracing was the film production, in the film industry. So a full ray tracing, because part ray tracing was done before, but a full ray tracing first time was done by James Cameron in Avatar in 2010, just 9 years ago. It wasn't real time. It was batch, which means you create each single frame, and then you have a sequence of frames and you get animation. Now to generate one frame in a server with 50,000 CPUs, it took 42 hours. It was just 9 years ago, 42 hours. Now this is a very heavy picture, because you cannot see, but there are many, it's not humans, but creatures are down there, some thousands of them, and you have a jungle and so on. So this quite, it's not simple. So it took time, but a lot of time. And then in 2013, we had by Pixar the first full ray tracing picture by Pixar. It was Monsters University. But this is still batch. So how do we get to real time? This is real time toward gaming. So the major step into real time was by creating a hybrid ray tracing. Hybrid ray tracing means you make kind of composition between raster and ray tracing. You make the primary rays by raster, and then all the bouncing stuff, all the bouncing rays are done by ray tracing. This is the way hybrid ray tracing is done. So The first one in 2011 was Silicon Arts. It was a small startup, Korean startup. They designed a speed-up hardware in silicon to speed up ray tracing. Okay? Then in 2014, a bigger company, Imagination Technologies, they produced a GPU which has a hardware in it which speeds up ray tracing. This is special purpose hardware. Now, it was a kind of try. It wasn't very successful from the market point of view, but a year ago, in SIGGRAPH, NVIDIA announces a ray tracing GPU. This was the revolutionary step. And this ray tracing GPU is based on a GPU, a hardware of GPU, and an extra hardware, two pieces of hardware, one to speed up the ray tracing, and the second one to denoise. Because as we will see, there is a lot of noising in GPU. How you denoise it? So this is done in hardware. This is what they get, is a GPU piece of hardware which is 225 watts. High power, so it goes to the high-end PCs, high-end. And the first debut was done right after that to first games with Unreal developers and so on. The same time, in the same SIGGRAPH, a small Israeli company called Adshir showed something else, a real-time ray tracing, which needs only 2 watts. It's a kind of miracle. I hardly believe, but exactly what happened. And this goes for not just for the small platforms, but it goes also to high-end platforms. So this is a kind of multi-platform solution for gaming. We will see. If we look at the picture here, this is very a nice picture because it shows here is raster, over there is raster, the middle slice is ray tracing, so you see the difference. We saw it in the video as well. Now let's talk about the challenges in ray tracing. Why so complicated? So first of all, we have big data structures in ray tracing. You have billions of rays. Each ray has to go through a data structure. Now, the data structure is a structure of triangles, of millions of triangles. Looking at the blue stuff, this kind of scene which is divided into small parts, and then you put these parts into a structure like this one, okay, binary structure. This is very small, just to show the idea. But the structure are huge structures. And then you have make what is called traversals. It takes time, a lot of time. About 80% of generating a single picture takes traversals of these structures. So it's very expensive. Now, there's another problem in ray tracing. The primary rays are simple because they are coherent. What does it mean coherent? Rays are going from the same camera and going more or less to the same area. If you take 16 rays or 64 rays, they go to the same area. So they undergo more or less the same way. So you can process them in parallel, okay, by SIMD hardware or whatever. Every GPU and every CPU has this kind of structures. So you can process it in parallel, very nice. But when you go to secondary rays, it's a disaster. Why disaster? Look at this picture. The red lines represent secondary rays. They bounce all over, so they are not coherent. So then the problem starts. You have to process them not in parallel, but individually. So that's a problem. So this is the second problem. The third problem is noise. Ray tracing generates noise. I don't want to talk about it. Why? Because it takes time, but let's see it. So this was the dynamic scene. Dynamic scene generates noise, and you have to denoise it, so it takes time. Now think about animation. Can you make animation, real-time animation with this stuff? No, that's a problem. So that's why in animated images, there's a problem of noisy film grain, okay? So it lowers the quality and also the performance. And the biggest problem is, remember the data structures, the big data structures? For animation, what is animation? Animation is actually change of the scene. You change the scene because the character is animated. Now I'm talking about what is called skinned animations, when the character can move the hand and so on. It's not just moving something from one place to another place, but skin animation. So for skin animation, you have to rebuild the scene for the movement of the characters. Now, what does it mean, rebuilding the scene? It's much more heavy than just making frames. So you cannot animate. These are the problems in ray tracing. Now, let's go back to Adshir. Adshir actually targeted the animation problem with changing the accelerating structures. The current acceleration structures are static. So I can represent them as a static cube. They're static. So what we've done, we've changed them to dynamic data structures, which are proprietary and which are protected by 30 patents today. So this is the huge step forward in ray tracing. What we got is, first of all, skinned animation for free. You get skin animation, you get animation. You don't have to rebuild the structures. The structures are exactly the same. So you get for free the animation. Now, the complexity is much less because you don't have these big structures. So this is less complex, which means the price is lower, the performance is higher, the power is lower. We will see it. So we have low cost, low power, and above all, this is a software solution, which means that you don't need hardware and accelerating hardware. You don't need special purpose hardware. You can use the GPU as it, off the shelf. And of course, you can use, if this is software, you can use any GPU for the same. So this is hardware and vendor independent, cross-platform. And this is compatible to game development engines like Unity, like Unreal and others. And this is the first time we get a real-time ray tracing on small platforms, okay? Which is different from NVIDIA. Now the question can be asked, very nice, it's very fast, but is it a good quality? So let's see at these two pictures. More or less the same pictures, maybe the angle is different, but more or less the same pictures, with more or less the same photorealistic quality. Okay? Non-animated, static pictures. Now, the upper picture is generated by V-Ray. V-Ray is a leading ray tracing software. And it took 40 minutes to generate it. The other one down there is by Adshir, by Local Ray, that's the name of the ray tracer. And this is done in 17 milliseconds. 17 milliseconds, which means this is real time, and this is 60 frames per second. This is the difference. So the quality is more or less the same. So first of all, I want to show how is it working on a mobile. So we're using, for this example, we're using Microsoft Surface tablet. Tablet is a mobile. You will see this video is a video of a demo that will be shown later on, 6 o'clock, I think here. 40 frames per second. You will see real-time skinned animation. You will see dynamic reflections, reflecting all over. And you will see that there is no noise. So this is on a tablet. This is augmented reality. So you see, there's a table with a mirror, with a marker, and this is how it looks, how the augmented reality looks from a tablet. This is real time. You see reflections, you see shadows, you see real time. They're dancing here, Michael Jackson music, but we cannot hear, but that's what they're doing. Michael Jackson would have been very proud of it. And this is 40 frames per second. Now let's go to, this was on the tablet, on the mobile. Now let's go to the high-end PC, and we are going to see something which is of a quality of, has the quality of a standard video game. So it's high quality, many reflections. It also has self-reflections, which means you will see a lady, a robot lady. Self-reflections means that not only the environment reflects on the lady, but also the hand and so on. So this is also self-reflection. You will see that there is no denoising and skin animation. What happens? There are 3 screens around, and you see the effect. We're going, yes, okay, so let's go on. Cross-platform capability. We say that this is software, and this software runs, it was tested and proved on different platforms, starting from PC, high-end PC, consoles, PC and consoles, laptop, tablet, and smartphone. And there are names of the machines. So let's go back to the cloud. So what we get? We get a strong self-sufficient client. First of all, cross-platform ray tracing. And then you can have PC, mobile, console, and so on, as we said before. And you can have many similar smart clients. For example, for consoles, this is something very important because a console vendor has millions of same clients. And if the client is intelligent, you have much less data to move to the client. Of course, you save a lot. And from the server point of view, there's low cost because they are off-the-shelf GPUs. You don't have special purpose hardware GPU. No hardware accelerators, of course, and doesn't have to use new GPUs, new infrastructure, can use the existing one. You can get a large number of concurrent online streams because of the intelligence of the clients, and power efficiency. This is very important. The power is low, much lower. And of course, the 5G connectivity will help in lower the lags and fast throughput. And we are approaching the last slide. And where are we heading to? So ray tracing is becoming the mainstream in graphics. This is something that nobody dreamed about it a few years ago. If you look at this, in 2019, ray tracing is about 10% of graphics. Not in gaming, in graphics, all graphics. And in 2022, it's going to be 50% and then 60%. So it's going very fast. I can assure you that once you play with a ray tracing game, you won't go back to regular raster game. So that's the point. And you see, Financial Times 3 months ago says that ray tracing expected to spark a graphics revolution in video games. Okay, so we believe in that. So it's not holy grail anymore. This is a reality. Thank you very much.